Benedict. So now he's going to get into interesting stuff. Not that the other parts are not interesting. So yeah, Benedict, take it away.
Let's get started. Okay, so let me just start with a quick recap. So I just want to kind of summarize what we did in the first 6 lectures. So we now know how to calculate the following quantities. So remember what we did? Okay, one is just the effective potential t equals 0. That was the first thing we discussed. Then we discussed the effective potential at non-zero temperature. And now the last thing in the rest of the lectures was how to calculate the decay rate from some false vacuum state to the true vacuum state. By the way, one thing I didn't explicitly say here is that so when you calculate the Lorentz action, like the potential appears, right? And of course you're not supposed to use the corrected potential. So not the tree-level potential, but like the finite temperature corrected potential. It's the effective potential should be calculated. It's actually a little bit tricky to show why this works, but yeah, this is the right thing to do. So use that when you calculate the decay rate. Okay, good. So now so far everything was implicitly or explicitly in Minkowski space. So now let's switch back on the expansion of the universe. And I just want to give you a very quick reminder of some important quantities that you encounter in cosmology. And then afterwards we're going to discuss parameters that characterize those sort of phase transitions. So that's the new section. Parameters. First order. Okay, and again, so a quick reminder. Some results from cosmology. So so we must change the metric from Minkowski to the Robertson-Walker metric. That is just the line element is given by this minus. So it's essentially looks like the Minkowski metric, except that there is a scale factor in front of the spatial part.
It's a square.
Is it? It's a square. Okay, and then from there you can define the so-called bubble rate. Which is just the time derivative of the scale factor divided by the scale factor. So this dot here is, I'm going to use it for the time derivative. And that kind of measures the rate of expansion of the universe. Okay, so then the next thing is the Friedmann equation. So you plug this into the Einstein equations. The energy momentum tensor, and then you get the Friedmann equation, which allows you to calculate the Hubble rate as a function of the energy density in the universe. So this is Newton's constant. And that's rho, and rho is the, well, let's call it rho out for total. So rho total is the total energy density. And there's three possible components. One is like battery relativistic stuff, which is called radiation. Then non-relativistic stuff, which is called matter in the context of cosmology, and then in principle also a contribution to the cosmological constant. I would just ignore matter here because we are at very high temperatures, so for most situations it's a good approximation. Otherwise it's also straightforward to change. So if you only have radiation, then you have contribution from radiation. T is the temperature. This we can call radiation. These are number of degrees of freedom in your sector, which for the standard model at very high temperature is roughly 100. So we have contribution from radiation, and then in general for the case of first order phase transitions, there can also be a contribution to the vacuum energy. And this comes from the fact that, it's a little bit more later, so just the fact that you kind of, if you're sitting here, there's an energy density between here and here, and you tune, because this is what you have at light times, right? So your cosmological constant should be tuned to more or less zero down here. So meaning if you are here, you have kind of like a positive contribution to the CC. Yeah, the last thing about this review, this lightning review of cosmology is useful relation, the time derivative of the temperature. So if I only have relativistic stuff, then the temperature scales like 1 over the scale factor. So I can write this as dET. Some reference temperature divided by the scale factor, and all the time depends on the scale factor. So this is some constant reference temperature. Okay, and now I just use I use the definition of the as a dot over a squared TR this is minus H.
Yes. There when you call the radiation, is it only photons or do you have?
No, it's everything that is unrelativistic. So in the standard model, gluons, photons,
Not the fermions.
Also fermions, everything. So everything for which you can neglect. So matter is really particles that are non-relativistic. So it would be standard model fermions at late times when they have lost enough kinetic energy.
So are not the quarks are there or quarks like quarks?
So this is just the cosmology lingo, right? So radiation really just refers to stuff that's relativistic, independently of whether it has a mass or not. You can
Different quantum numbers.
exactly. So it really just matters that it's that the kinetic energy is much higher than, or the temperature is much higher than the atmosphere. So it's just a standard lingo in cosmology.
And you're considering temperatures of the order of 100 GeV.
Exactly. So
So almost everything except top quark maybe is relativistic.
Yeah, now it depends on. If you are, as long as you are above the electric scale, then everything's massless anyway, right? Because it extra energy.
Oh, that's right. You have thermal masses, but that's another.
You have thermal masses, but those are, a different thing.
Yes.
Yeah, exactly. So I have temperatures in mind between 100 GeV and far above, right? So I haven't specified anything yet, but in principle, there's the temperature range here. But it's also straightforward to generalize. You can add another component. If you have non-relativistic stuff, you just add another component. Things that do change a little bit maybe, but it's straightforward to calculate. Okay, so now I just want to go through some parameters that are important for first order phase transitions. And the first thing is the so-called critical temperature. I think I've mentioned that already a few times, but let me just properly define it. So as we discussed, but as we saw, if I have the effective potential, some field phi, typically at very large temperatures, now let me already call this Tc, the potential, the thermal corrections are such that the minimum is really at the origin. So now I cool, and then what happens in first order phase transitions. So let's call this T1. Then at some temperature T2, which is still much larger than Tc, but now less than T1. Cooled a bit. Kind of find that there is like a second minimum appearing. And then eventually these two minima will be equal. And the temperature when this happens is what I call the critical temperature. So potential at Tc looks like this. Tc is the temperature the two vector equal. That's kind of, from there on, I can have a phase transition, right? I mean, now still it's not really possible, now I cool a little bit and this goes down, and now in principle, there's the possibility of the field which is still stuck here, right? Because it was initially stuck here. The way I drew it is this should be at the origin. So it's still stuck here and then down to the center. Okay. So now the phase transition is in principle energetically possible, but it doesn't mean it happened immediately. And the start point at of the phase transition is usually called the nucleation temperature. So let me, okay, so we know how to calculate this decay rate, which is kind of essentially you can think of it as a rate per unit time, per unit volume that these bubbles now appear, right? So that the field tunnels in a given region. So now I want to turn that into the number of nucleated bubbles per Hubble volume. And the Hubble volume is just given by the Hubble rate to the minus 3. Okay, how can I do this? So we call this n. So this is like the expected number of bubbles per Hubble volume at a given time. And so to do this, I integrate from t minus infinity to the time. The integration variable, and I take the decay rate. Now, in principle, the decay rate is a function of the temperature, but I can always express temperature as time. And now I will actually do the inverse in a second. So you can think of this as a function of time. Multiplied by the Hubble volume, and that is integral.
Which is also a function of time. Which is
Hubble, yeah, Hubble of course is also, you can, so exactly, so let's write this. Okay, but now what I will do actually is I will do it is let me just use, well, I guess I have this relation with d, the time derivative of the temperature with respect to the temperature with respect to the time. I got this factor of minus Hubble rate times temperature. Okay, and then I can express this as integral from. Variable, so let's call this the number expected bubbles as a function of the temperature. That's the integral from t to infinity. Now I re-express it as a function of the temperature, and the hover rate also expressed as a function of the temperature.
This time t that you put in the integral is the same t from co-moving observers in the Robertson-Walker metric?
Yes, I mean I guess in in the rest frame, right? Yeah, really, yes.
But then shouldn't it have some lower bound instead of going all the way to minus infinity? Because you're going backwards in time and you expect to, at some higher energies, to reach a singularity.
Well, but you reach it at t minus infinity technically, right? So
no, it's a finite.
I mean, yeah, as you will see, it doesn't really I mean, this boundary doesn't really matter. So I mean, I can also put it at some lower value. So I guess there's a conceptual issue. I'm not sure there's a conceptual issue, but if there is, it doesn't. Technically matter. So
Okay.
you can think of it as a formal definition. I'm not sure. So why are you saying you cannot? Yeah. Okay, it could be. I don't know. Okay, so, and then we define Tn by the condition that the number of bubbles per Hubble volume is 1. So this is kind of the temperature. So typically what happens is that, okay, again, like at high temperatures you cannot tunnel at all, right? Now that here, then you reach your critical temperature. And then energetically it's possible to tunnel, but then typically the barrier that you have in this sort of phase transitions is so big that the tunnel rate is very suppressed. So you have to cool a little bit more. And the more you cool, the lower becomes your barrier typically. And so the decay rate goes up. So it grows very strongly with the temperature. Yeah, and then kind of at some point it becomes so big that this integral becomes 1. And then actually what is usually enough is to just oppose that gamma of Tn is kind of 1. And that's what actually most people just do. So you kind of use the fact that this is kind of growing so quickly with temperature that
It's actually age minus 3 on the right hand side.
sorry?
Because of the dimensions, just because of
No. So this has dimension 4, right? That's decay rate per volume and time.
Okay, so it's not a decay rate per se, it's a decay rate per volume. Okay.
Yeah, exactly. It's a decay, so it's decay per unit time and volume.
That's
so,
right.
yeah.
Okay,
So that's dimension 4, so this is dimensionless, and then this is dimensionless.
Sometimes I see the decay rate is just compared to the Hubble rate, but that's not what you're doing. So this is kind of confusing sometimes.
Well, I guess maybe what people...
that's the interaction rate, the gamma you are thinking.
Yeah, exactly, that's the interaction
rate, which is the real rate.
Or, I mean, if you want, you could define the decay rate per Hubble volume, so you can get rid of like 3 powers of h here, redefine this.
Okay.
Okay, so let me just quickly. Okay, so typically, I mean, you have to look a bit at how this depends on the function, the temperature, but typically gamma grows so fast that kind of it's enough to actually just consider this condition. That's what most people do. So it kind of, I mean, intuitively, you can think it's kind of the temperature where this Hubble rate, the decay rate can compete with the Hubble rate, right? So you're comparing two rates. Kind of the same order of magnitude. Let's start to appear in significant numbers. So you can turn this into a criterion on your bounce action. So for those 3 symmetric instantons as an example now, it's like IFAE determinant, and then I said you can make an order of magnitude estimate. What people typically do is they just set this equal to the temperature. So, and again, the dependence on this factor is not so, the influence of this factor is not so big. What really matters is kind of the size of the bounce action. That's a much more important quantity. So you approximate this prefactor by 2 to the 4. And now, okay, now you can do it, if you want to do it at home, you plug it in, use the formula I had for the hover rate before, and what you find is the following criterion: S3 En. So the bounce action divided by the temperature value at the deviation temperature should be 145 minus this small dependence on the temperature again. So you can kind of you can calculate your bounce action as a function of the temperature, right? I told you how to do this in principle, and then you go down in temperature, and once it reaches 145, you have to take into account a little bit this correction term. The decay rate is so big that you can create one bubble volume, and the phase transition will start in earnest.
So here you made some assumptions on the degrees of freedom, right?
Hmm?
You made some assumptions.
Yes, exactly. So here, exactly. So here I assumed that 100 degrees of freedom, exactly. So just the starting model, exactly. So I think the influence is probably, I don't know how well it enters. I guess here in the log, so it's probably mild anyway. So, and I also neglected the vacuum contribution to the in.
You probably did.
Yeah. Exactly. So I also assumed that the vacuum energy doesn't dominate yet. But again, it's straightforward to modify it if the assumptions are different. So exactly. So. Right. So if you look in the literature, that's a formula that you will see often. Okay. So the next parameter that I will define is called beta. So beta, let me just write. Beta can be defined as the logarithmic, the time derivative of the log of the decay rate, or the time derivative of the decay rate divided by the decay rate.
That's a terrible name, no? Because beta is 1 over t.
I didn't come up with this. Yeah, you're right. Exactly. So exactly, don't get confused. Beta is in some parts of the lecture 1 over t, and now it's d gamma dt over gamma. So. Exactly. So, and so
I think it has the same dimension than the current beta. It has the same dimension.
yes, exactly. It is. In that sense, it's consistent. But it's not actually. Yeah, it's very far away typically from the temperature that you have at the point. So. So in that sense, there's nothing to do with the temperature. It's a function of the temperature, as you will see in a second. So, okay, this tells you how fast the decay rate now grows, right? So, and thereby gives you an estimate of the length of the duration of the phase transition. So beta is a rate, so beta inverse is an estimate of the duration of the phase transition. Because once the decay rate, the tunneling rate is very big, and essentially everything is filled by bubbles, right? And then the phase transition has completed. Okay, so now we can just again rewrite this a little bit. So first I change my dependent variable, so I go to, yeah, sorry, and I should say this is evaluated at the time of nucleation. So the time of nucleation is time of, and it will become a bit clearer in the next step. So the time when I have on average one bubble per Hubble volume, then I evaluate this, and this gives me an estimate of like how long the phase transition then will take after this started. So okay, I can change the dependent variable to temperature by using this. And now it's clearer, like it's evaluated at the nucleation temperature. Right? So now let me make ansatz for the decay rate. So I call this prefactor A of t, and then I have an bounce action in the exponent. Okay, then if I evaluate this, what I get is hd d plus dt minus hd nucleation temperature. Just plug this in. Okay, now you see that kind of because this, essentially because this enters in the exponent and this doesn't, this depends here, and you have the derivative of the log of the prefactor, whereas here the derivative of the action. So typically this is much less important. So I can neglect this piece. I can just replace it by ht d plus e dt. Evaluated at the nucleation temperature. So again, now we know in principle how to calculate this. Okay, it's a bit more useful to write this in a slightly, so now let me write it in a slightly different way. So beta over h at Tn is Tn is the and so kind of one thing you can maybe learn from this if you calculate it. So beta of h is a dimensionless number, and in all situations that we consider this will be larger than 1. Well, at least 10 or even larger. In this case, so you see that kind of this tells you in this situation the phase transition is short compared to the Hubble time. So you can essentially, for the purpose of the phase transition, you can neglect the Hubble expansion. So let's say this beta over h at Tn much larger than 1. Another way of phrasing it is that phase transition completes at temperatures very close to Tn. Because it's fast compared to the Hubble time, so the universe is essentially static while the phase transition takes place, so the temperature doesn't change. So. If beta or h is much less than 1, which can in principle happen, then you have to be a bit more careful, but don't consider this here.
Well, the supercooling is exactly that, right?
Yeah, supercooling, even in supercooling, it's kind of, you can easily stay. Supercooling typically, you can go down even further, but it's enough to kind of for our purposes to go down to beta of h order 10 which is already quite small. So like, if you don't have supercooling, beta over H can be 1,000 or 10,000 or even bigger. So the supercooling already brings you into this regime, but you can bring it even further. But I mean, it's enough for us to stay in the regime where beta over H is order 10 or larger. The next parameter is called alpha. Very creative. So yeah, as I said, so we kind of have this situation typically where, like, once we tunnel, so we go from here to here, that's the potential. There's typically some energy gap here. So this latent heat that's released during the phase transition. So let's calculate this. So this we call delta V. And now this is, as I mentioned before, the effective potential is the free energy. So this is kind of the free energy difference between the two right here. What we are interested in really is the energy density difference. So we have to change this. So and just some basic formula from thermodynamics tells us that the energy density or the energy difference is the free energy difference plus temperature times the entropy difference. And again, everything is evaluated at the nucleation temperature because that's where the phase transition takes place. Okay, so now there's a free energy, so the entropy is obtained by the derivative of the free energy with respect to the temperature. So this is delta V minus T T. Like this, and then you can see how it changes with the temperature. That's the second piece, the term derivative. Okay, but this was maybe a little bit unnecessary detour because in general this is kind of, you can neglect this, and especially super good phase transitions because the temperature here is quite small. Typically you can just neglect this piece and this is delta V. So approximate the energy density difference by the free energy density difference. Okay, and then we define alpha as the difference in energy densities between the two vector divided by the energy density in radiation. So this is a measure of kind of like, that's the energy density that you have in a thermal plasma during the phase transition, and that's kind of how much inhibition you put into your system. And that will be an important parameter like later when I discuss gravitational waves. Okay, so. One parameter, this is so-called reheating temperature. H. So, especially in supercool phase transitions, which we'll see on Monday, are the ones that are most interesting for the purpose of gravitational waves, at least at the moment. So for supercool phase transitions, those are phase transitions that again take a lot of cooling it requires a lot of cooling to reach a decay rate of the order of the hover rate, or hover rate to the fourth power. So it takes a lot of cooling until the phase transition actually takes place. And that means that kind of like this here is much smaller than this here, so alpha is much larger than 1. But define supercooled phase transitions as those that have alpha much larger than 1. Equivalently, where the energy density between the two vacua is much larger than the energy density in radiation at the time of the phase transition. And then, so it means that you can now inject a lot of extra energy into the system, right? So, which means that this energy will be converted into thermal energy. So you heat up to a higher temperature again. That is called the reheating temperature. So the energy released during the phase transition reheats the plasma to some temperature T reheat, which is much larger than the temperature that you had at the time of the phase transition, which was the nucleation temperature. And you can calculate this approximately, just to make it more quantitative. So the total energy that we have now after the phase transition, so we had the energy density in the thermal plasma, and now the energy density in the vacuum is converted also into thermal plasma during the reheating process. So we can equate this Tn with the energy density in some thermal plasma at the reheating temperature. This assumes kind of that this conversion process is instantaneous. It's a bit debatable whether that's a good approximation or not, but it kind of assumes that. Yeah, so I mean, first what happens is that the energy density goes into bubbles, right, and into like thermal motions of your plasma, but then at some point the whole system equilibrates and you end up with a thermal plasma at this temperature TRH, assuming that it happens very fast, then you can just equate the two sides straight.
Actually, you can probably neglect the low radiation in the first.
Exactly, yeah, principle. Well, depends a little bit how much you supercool. In the limit of extreme supercooling, you can plant it. Okay. The last quantity I want to discuss, and then we can talk a bit about gravitational waves.
I think I've just lost. Just can you recap? We are doing the phase transition, then we are going from the false vacuum to the true vacuum.
So,
Then again, delta V potential, which is converted to temperature to reheat plasmas.
So we are kind of again. So at very high temperatures, we are here. Right? The potential looks like this. Now it goes down, and at some point, we reach a critical temperature where we can tunnel. It goes like this. Now we cool even more, and the potential starts to look like this, where there's like a big difference, a growing difference between the free energies here and here, which essentially, like, typically is the same, say showed here, as really the energy difference between the two vacua. Okay, and now the universe tunnels from here to here. So what happens is you form bubbles in certain regions of space. Right? These are the regions where you have already tunneled. Outside you haven't yet tunneled. These bubbles then expand. Then there are other bubbles, they collide with other bubbles. And eventually, like, everything is in the true vacuum, so the whole universe is here. In this process you release kind of this energy density difference, right, into your system. So, and this has to go somewhere, and it goes into just thermal energy. I mean, right? So, and
Just an adiabatic process.
An
adiabatic process.
Right.
This energy is released.
question exactly now? Like the
I was just figuring out where the heating temperature came from.
so the heating temperature is really now under the assumption that kind of this whole process happens very fast compared to the Hubble time. I think that's a relevant time scale here. So kind of this bubble collisions and then the redistribution of the energy density into thermal energy density happens very fast. Then you can essentially just use this equation here, which is this energy conservation. Right? So you just equate the energy that you had before with thermal energy at some temperature after it has equilibrated. If it takes more than the Hubble time, then you have to, then things become more complicated. But that's also typically what people do. So there's a lot of simplifications here. Okay. So the last quantity I want to discuss is the bubble wall velocity. No, not necessarily. So, as I discussed last time, so when we had this discussion about the O4 symmetric instantons and the bubbles, exactly, there was one. But as I think I also said at the time, this was assuming that I'm an absolute vacuum, right? So now if I'm not an absolute vacuum, if there's thermal plasma interacting with the bubble wall, it can slow down the bubble wall. Simply by, just there's friction, right? It goes through this plasma, so this slows down the bubble wall. From my description, I think it's already kind of clear that this is quite difficult to calculate. Still a very active field of research. So it's called VW usually. It's very difficult to calculate. Because you have to, it's essentially a non-equilibrium process, so you have to kind of take this into account, the interactions between the bubble and the plasma. So all I want to say here is that there are three important regimes that you can distinguish. One is the possibility that it's just non-relativistic, so the velocity is much smaller than the speed of light. That could happen if the interactions with the thermal plasma are so strong, the friction is so strong that it's slowed down so significantly. Another possibility is that it's relativistic, but it doesn't run away. So this is what that means, but not run away. So that means that the velocity is very close to 1, but the gamma factor approaches a constant. So the gamma factor is 1 minus velocity squared, approaches a constant. So the bubble wall reaches speed of light essentially, but it doesn't keep accelerating. And the third possibility is that it's a runaway bubble. Runaway. So the V is 1, and the gamma factor V squared measures. Of course, it doesn't go to infinity, but kind of during the whole phase transition, the gamma factor keeps increasing. And as I will tell you later, these three regimes are kind of important for the kind of gravitational waves that you produce. So they allow you to distinguish different production mechanisms that are dominant. So there has been a very important new result in 2017 by two guys called Benedict and Moore. It was in Germany. And they showed that they're typically, so in theories with gauge bosons, which includes the Higgs, right, for example. So in theories where, sorry, I should be more specific. In theories where the gauge boson gets a mass when crossing the bubble wall. So crossing the bubble wall means, like, again, outside you're in the false vacuum, inside you're in the true vacuum. So for the Higgs case, it means that outside the Higgs value is 0, inside the Higgs is non-zero. So a gauge boson that can interact with the bubble wall is massless outside and massive inside. Right? And if you have such a situation, then the friction force turns out to be so strong that this regime is almost impossible to reach. So the bubbles will always reach at most a relativistic non-binary regime. So they stop accelerating, they reach a final terminal velocity at some point during the phase transition. Yes. I don't know if you're interested, so this is difficult to reach. If you still can read this, Bödecker and Moore. Sure. These lectures, it's enough to remember that as long as you have the situation with the gauge boson requires mass across the bubble wall, which also happens in the common Weimer model that we discussed. So, and of course in lots of other models, this is very difficult to reach. And I will tell you why this is important in a second, but first let me now go to the next section. We are ready to talk about gravitational waves. So, gravitational waves. From first order phase transitions. So there are three main production mechanisms for gravitational waves in first order phase transitions. The first one is just collisions of bubble walls, right? So again, bubbles form in different parts of the universe during the phase transition, then they expand, and eventually they will collide, right? And this collision is kind of a violent process, and this can lead to the production of gravitational waves. Bubble wall conditions. And in front of the bubble walls, when the bubble walls expand, there's still a thermal plasma outside, right? And so the bubbles, as I said, they interact with the thermal plasma and they lead to kind of sound waves propagating through the thermal plasma. And then after the bubbles have collided, like the whole thing is just, you can think of it as like wobbling around, like you have these sound waves propagating through your plasma. Sound waves can also collide with each other, and that gives another contribution to gravitational waves. And then at even later times, there's a possibility that you reach a regime where the whole plasma develops turbulence. And that can give another contribution to gravitational waves. This production mechanism is, first of all, much less important than the other ones. So typically, I think it is assumed that this turbulence contribution is about 10% or less of the contribution from sound wave collisions. And it's also much less well understood, so I will just leave this out here. It's less important. So less important. And also less well understood how to determine the spectrum of gravitational waves on the side. Just leave that out here. Yeah, so and I can actually already say now that kind of make the connection to the discussion here about the bubble wall velocity. So it turns out that kind of in this relativistic non-runaway regime, the dominant contribution comes from sound wave collisions. Essentially because the energy density stored in sound waves grows like the volume, and the energy density in bubbles only grows like the surface of the bubbles. This is kind of located in around the bubble walls. So if you don't reach this runaway regime, you can show that kind of the sound wave contribution is the dominant one. If you reach the runaway regime, you will also have an important contribution from the bubble wall collision. So already kind of one important distinction. So this changed kind of, so this paper by Benedict and Moore now changed a lot, like what people are assuming for the spectrum.
08215.
Sorry?
Archive.
Yes.
I remember the number.
Already, okay. Very impressive. Thank you. Okay, so now I want to talk a bit about gravitational waves. Okay, I think I can still get where I wanted to get today. But yeah, since time is kind of short supply, I will take some significant shortcuts. The starting point of every calculation in GR, I guess, is the Einstein equation. So these are kind of the tensor, which is scalar, and the energy moment tensor. Okay, so now we want to, we want to study gravitational waves, which we think of as kind of ripples around flat space. So we're expanding the metric around Minkowski space. So we're making this ansatz. G mu is equal to eta mu. And now again we are neglecting the expansion of the universe for simplicity, plus some small perturbation h tilde mu. H tilde is much less than 1. And now it's convenient to define the so-called trace reversed perturbation. The name is pretty obvious once you see this object. useful to impose what's called the Lorentz gauge. So, like for the gauge bosons, the gravity has some gauge degrees of freedom, and you can in particular impose this condition.
I'm confused by this is the second term.
Yeah, sorry, this is of course not good. So this is the trace of this object. So rho sigma it's an object. So it's a trace of this object. Okay, and then so kind of you work this out, and I invite you to do that at home. And then you find that this satisfies a wave equation. Looks very similar. So this is 16 Newton's constant. So it satisfies the wave equation that is sourced by the energy momentum tensor.
There's also a pi. A pi. I guess you forgot the pi.
16 pi. 16 pi.
Could be, I don't know. I don't have it here, but I believe it.
Dimensional reasons.
Eventually.
Pi g.
IT, okay. Yeah, it must be because I have a pi in the, I mean, I have a pi here, so of course I have a pi there. Question yes.
Why would you expect that it's a good approximation to just neglect the expansion of the universe and use perturbation around a flat metric? Is it because the time scales here are fast compared to the...
Exactly, so I mean, as I told you, right? So, okay, at least for the purpose of gravitational wave production, as I told you, like the phase transition is much faster than the expansion rate of the universe, right? So at least for this process, you can neglect it. I don't know if, I guess for binary inspirals, probably you cannot, well, in the final stage, yes, also, right? So, yeah. Okay, so let me hurry up a bit, because I wanted to get to some parametric estimate today. Okay, so now what I wanted to derive is the so-called quadruple formula. But since the derivation is a bit involved, and I'm short in time, I will just tell you some important intermediate stops on the way. And you're welcome to go through the calculation in more detail at home. So this equation can be solved exactly like in electrodynamics with a retarded Green's function. Remember electrodynamics. The Green's function is defined just as the function mu, the derivative acts on x, I guess, which is the delta function. Solve this. This is done in every electrodynamics lecture. Find that this is given by 1/4 pi. This is a solution that you find with retarded, like opposing retarded boundary conditions. Okay, and now once you have this function, it's very easy to solve this equation because you can just, if you now integrate the right-hand side over this kernel here, you get the solution, as you can easily check by just using this equation here. So, fine, is that the perturbations that are generated by a given source, given energy momentum tensor. This is also quite good. It's just given by the spatial integral over the energy momentum tensor. Okay? So, I mean, if you check, if you act with this on this, then this equation tells you that on the right hand side you get this expression here, right? Then you have to integrate. Yes. Yes, exactly. So, acting with the D'Alembert operator here and here, using this equation, you see that you just get two. So,
No, I'm not sure about the pi, because you have a pi Green's function. So.
Now the pi simplifies. the pi
you're right, I think here the pi is gone. So just okay, look, I will not actually use any, I mean,
Pi equals
I will
1.
very, you will see like in a few minutes I will use this equation and do violence to it. I will use like, I will do some.
Units of pi.
Hmm?
Do it units of pi.
Exactly, units. I said like natural units for pi is 1. Yeah, no, I will not need this level of precision actually. So. Okay. Next step is to kind of look at this in the so-called far-field approximation. So the idea is we have some localized region where the energy momentum tensor is non-zero, and we assume it's zero everywhere else. Okay, then we can kind of y is my coordinate in this region, and x is kind of the coordinate, the vector pointing to the observer, which is here, like very far away. Okay, then I can make this approximation that approximately 1 over x, right? So I just neglect the y. And we call this, so we call x r, just for simplify the notation a little bit. Okay, so then I can write this as minus 4g over r. The r now doesn't depend on the y anymore. D mu minus r2 y. So, and now let me introduce so-called quadruple moment of the 0-0 component of the energy momentum tensor. So, quadruple moment is given by J integral over the 0-0 component of the energy momentum tensor, and then times yi j. This you probably should have seen already in electrodynamics, where you can do different monopole, dipole, quadrupole, and so on and so forth. So this is the quadrupole moment of the 0-0 component of the energy momentum tensor. And now I will again take a shortcut. So I will just tell you that, so now you can use the fact that using that the energy momentum tensor in the gauge that we chose satisfies this equation, so it's a wave conservation equation. And this you can easily show from the fact that, so remember the wave equation looked like this, with the alpha h mu roughly t mu. And now you act with the derivative on both sides. And now use the fact that we chose a gauge where d mu acting on h d mu is 0, so you see that this side is 0. So use this, and you also partially integrate a couple terms, and then you can show the following relation. And now I'm kind of focusing on the spatial components of the metric, because these are the components that give you the gravitational radiation. Minus 2g over r. J. So, again, this is actually very easy to show from like essentially going from here with this definition to here. You can do it like in half a page if you want to. Just use this identity and partially integrate a couple of times, and then in this way get the time derivative then. So this is a very important formula. This tells us that what sources gravitational waves is a time-dependent quadrupole moment. So if you remember in electrodynamics, if you have a time-dependent dipole moment, that is already enough to source electromagnetic radiation. So you have like a charge which kind of moves along a rod up and down, that sources electromagnetic radiation. For gravitational waves, this is not enough. If you have a mass that kind of like just moves up and down like this, that doesn't source gravitational waves. So what you need is kind of like a time-dependent quadrupole moment to source gravitational waves. Okay. And now we are getting to the formula that I need for my parametric estimate. So now you can define an energy momentum tensor for the gravitational radiation. I think it's not actually really a tensor, it's called a pseudo-tensor, so it's a little bit tricky, this definition. And then using that, you can kind of calculate the amount of energy that is radiated away through, like if you have, again, it's like we assume that the source is localized in a region, and now I want to know how much energy is lost in gravitational waves per time due to, I don't know, something happening here, right? It could be like colliding neutron stars, or as we will use in a few moments, colliding bubbles, for example. Right? So stuff happens here with a time-dependent quadrupole moment, which sources gravitational waves, and the gravitational waves leave this region, and they take some energy with them. And this is so-called quadrupole formula, or maybe this is already called quadrupole formula. I have different notations, which was first derived by Einstein in 1980 already. That was at the time when he thought gravitational waves were real, and I think he changed his opinion again. I guess he changed it again, I'm not sure. So, the energy density in gravitational waves that is radiated away from like this enclosed region is given by g over 5. And then the third time derivative of the quadrupole moment. So this is some kind of time averaging that you have to do to make sense of this definition. And this is a projection onto the traceless component of this quadrupole moment. Again, I will not actually really need this level of precision. So. Okay. And now get ready for some very audacious estimates. So now I want to use this formula to make some back-of-the-envelope estimate of the energy density, or the energy that is kind of created in the form of gravitational waves during bubble collisions. So what I will consider, so again I will consider some enclosed region where I'm looking at a small number of bubbles that are colliding. And I will assume that they are non-relativistic for now. Later we can just extrapolate to the ultra-relativistic case, but for now just assume that the wall velocity, the bubble wall velocity is much less than now. Okay, and now I want to use this formula to kind of estimate how much energy is generated in this process in the form of gravitational waves. So essentially I'm using this formula, this tells me how much energy is lost, and then I integrate it over time, and I get an estimate of how much energy is generated in this process. And so how I do this is I use the fact that there's a characteristic timescale in this process, which is just beta inverse. It's the duration of the phase transition, as I told you. So this is kind of the only timescale that I have in the problem. So timescale beta inverse. Then the characteristic length scale is kind of the size of these bubbles, right? The size of the bubbles, in turn, I can estimate so that they have a certain size initially and then they grow, right? Because they expand with the bubble velocity. It turns out the initial size I can typically neglect. So I can just, as an estimate for the size of the bubble, at the end of the phase transition, I can just take the velocity and multiply it with the time scale of the phase transition. So, characteristic length scale is the size of the bubbles, which I estimate as wall velocity times beta to the -1, right? Okay, and now I make an estimate for.
The velocity, what is set by?
Well, again, this is as I said, it's difficult to calculate. You have to kind of, I mean, you just.
Yeah, but physically I can.
I mean, it's set by the friction of the plasma, the interaction of the plasma with the bubble wall, right? So.
And also by the energy difference of the two phases.
The energy difference depends a role. I mean, I guess but then also the number of degrees of freedom will play a role. The interaction strength with the bubble wall will play a role. I don't think there's a simple parametric, and there's no simple parametric estimate for the bubble wall velocity as a function of this. In principle, you have to calculate like in full glory, and it's very difficult. So at this stage, what people usually do is they just assume something for the bubble wall velocity, and then kind of show how, for example, gravitational waves, how they depend on the bubble wall velocity, and how sensitive your results are on your assumption for the bubble wall velocity. Okay, so now if you look, so this is kind of some kind of, so we are non-relativistic, right? So this is some kind of mass density, this T00 component. So if I integrate it over the volume, I can just think of this part here as a mass. So it's some kind of characteristic mass, the total mass of the bubbles, let's say, right? So I can write this, so because now I want to evaluate the third time derivative of this quadrupole moment tensor, because this is what enters into this formula. So again, so the quadrupole moment tensor, I can kind of estimate this piece, I can estimate and write as mass of system in motion, so it must be something that moves, of course, because otherwise you don't generate gravitational waves. And then I have this y squared here, which is of the order of the length scale squared of my problem. So times length scale squared. And now the time derivative, what does the time derivative do? Like just for dimensional reasons, I have to divide by the characteristic time scale, right? So really I'm just doing dimensional analysis here. And I have to divide by to the third power, right? Because I'm taking the third time derivative. So now if you so now if I plug this in, right? So let me do this here. So I don't have to rewrite everything. So we said the characteristic length scale was squared, and then that's beta to the minus 1 cubed. So in particular, you see that kind of you get mass of something times velocity of something squared in the non-relativistic regime. That's a kinetic energy. Right? So this is kind of the, you can think of this now as the kinetic energy that is kind of stored in the bubbles. So you can write this as energy, and then I still have one beta inverse left, so beta inverse like this. Two beta inverses are cancelled by the beta inverses in the numerator. Okay, so now let's get an estimate for this kinetic energy. So the kinetic energy is given by. So the kinetic energy, of course, is kind of the kinetic energy in the bubbles is now given by the latent heat, by kind of the, right? Remember there was some kind of potential difference. That's the energy that is released during the phase transition. So you can think of the kinetic energy in the bubbles is this energy density that is released during the phase transition. But that's an energy density. Now I have to multiply it with the volume. And again, like the only characteristic length scale here is the bubble size, right? That may make sense, right? So inside the bubble I have released this energy density, outside not, so I should multiply this by the bubble volume. And this I can now just, it's convenient to rewrite this using the definition of alpha. Remember alpha was delta rho over rho ret, the radiation, energy density radiation at the nucleation temperatures. I just rewrite this. Okay. So now we have this object. So now we can combine everything and get an expression. So we can estimate the energy density radiated away in gravitational waves. It's roughly Newton's constant times this guy squared. So I use this here. So I get alpha squared or rad squared 6, and there's a beta inverse, so I get a beta squared. Okay, now I'm using the fact that that I can rewrite using Hubbard's law. I just convenient to rewrite Newton's constant in terms of the Hubble rate squared at the nucleation temperature. So let me just over. So this is nothing. I'm just using Hubbard's law here to replace Newton's constant.
And that rho is rho rad, basically.
Sorry?
The rho total is basically rho rad.
No, rho total is
Delta
much,
rho, delta rho.
exactly. Rho total is much bigger, exactly, because exactly with rho total was delta rho, the essentially latent heat plus the energy density radiation. Okay. Almost there.
So now 8 pi equals 1.
Yeah, I mean, so I guess
Sorry.
100 equals 1 almost. Actually, not quite, as you will see. So it's actually remarkably correct, remarkably precise. So you'll see in a moment. So just hold your breath. Okay, so now this is the energy density radiated away. So now to get the total energy, we have to again multiply this with the characteristic timescale, beta inverse, right? To integrate, so essentially we are integrating over time. And now we want to. I can already do this, like this, times beta to the minus 1. And now I want to, what I really want to get at is the energy density in gravitational waves. So I take this, the energy that is radiated away, or produced during the bubble collisions, and divide it by, again, the characteristic volume, which is the bubble volume. So I define rho gravitational waves is equal to roughly the kinetic energy, the total energy in gravitational waves that is generated divided by the bubble volume. So ball velocity beta to the minus 1 cubed. And now it will be convenient to change the definition once more. So what we really want to know is kind of the omega gravitational waves, which is the energy density in gravitational waves divided by the total energy density at the time of production. Okay, so now I can just combine all this. So I'll let you do this at home. So I just use this. I use this definition for, I use the fact that I can rewrite Newton's constant like in this complicated way. That's useful. I divide by the bubble volume cubed and by the total energy density. And I'm also using the fact, so use that. Second, that I can write the total energy density at the time of nucleation as delta rho plus right, and write this as 1 plus alpha. Okay, so now I convert everything. What I get is the following estimate omega gravitational waves. Goes like, I forgot one thing that I have to tell you in a second. didn't mention is that, so in principle, so here in this relation I assume that the whole latent heat is converted into kinetic energy of the bubbles. But of course, that's not true. I mean, usually only a fraction is converted into kinetic energy, the rest goes just into heating the plasma right away. So I have to include some kind of efficiency factor here, kappa, that takes that into account. And then if I pull it through, I get a kappa squared here. Okay, so that's our estimate. Can I go a few minutes over time? I don't know, is it? Okay. Just to get to one final resting point. So that is the energy density in gravitational waves. Now, of course, they will not be radiated at arbitrary frequencies, but they will have like a peak frequency where the spectrum is kind of localized around. And again, the only time scale that I have in the problem is beta inverse, so the frequency of the gravitational waves will be of the order beta.
And beta can be very different from the Hubble scale?
Yeah, exactly. So it can be orders of magnitude different from the Hubble scale.
So it cannot exceed the Hubble scale.
Sorry?
So it can be, so the time scale is always longer than the Hubble scale or shorter?
I mean, in the scenarios I'm looking at, it's always shorter than the Hubble length,
Okay.
Hubble time.
So the Hubble time.
But in principle, you could also have the other situation, but I mean, then things become more complicated. So in principle, yeah, the frequency is lower than the Hubble time. Higher than Hubble time at creation. So Hubble frequency.
Yeah, because the Hubble is the biggest wavelength basically.
Exactly. So it's shorter wavelength to kind of fit into exactly. Okay. So the last thing I want to do before I stop for today is, so this is at the time of the phase transition, so the nucleation temperature, roughly. And now we want to kind of know what we can detect. We want to know what we can detect today, right? So we have to evolve these quantities to today. We have to redshift them today. So, and this is very straightforward. So, let me introduce labels. So, first of all, I'm splitting this omega gravitational wave into the rho gravitational wave and the energy density. Let me give it a label now. So that's the energy density gravitational wave today. So this means today. And so gravitational waves are just radiation. They're like photons, right? So they scale like photons. With the expansion of the universe being the energy density scales like the scale factor to the fourth power. So let's get this. A factor of divided. So this is at phase transition. The energy density of phase transition. I label this with index n, and the energy density today I label this with index 0, and then the same for the scale factor. So I just take the scale factor at the time of the phase transition and divide it by the scale factor today to the fourth power.
Which is 1 today.
It's arbitrary, right? So it's just
usually defined by 1.
Usually you can define it as being 1 exactly, but in principle it's all that matters is the ratio, right? So, okay, so the same I do for the total energy density. So total energy density today. And now I'm just using Hubble's law to do this because I don't really know how it scales. But it scales like radiation for a while and then it scales like matter again. So in order to not having to take that into account, I just use Hubble's law. That allows me to get this relation here. It's just the ratio of the Hubble rates at the time of the phase transition and today's squared. just write this down so that you can check it at home if you want. All these calculations are very simple. So I use the fact that entropy is conserved to a very high precision. Which gives me the following relation. So it's a number of degrees of freedom, which is slightly different from the one that I used in the energy density, but we need this level of precision again. Completeness. So this is relation. Entropy density at time unification is equal to entropy density today. No, total entropy because I'm multiplying those scale factor. So I'm using this, and I use that h squared is equal to, now I write Friedmann's law in terms of, essentially write Newton's constant in terms of time scale, because that's more. Five, 10 GP. I use the Hubble rate today, which is measured. This is little constant little h, which measures the Hubble rate in units of 100 kilometers per second in megaparsec, and it is about 0.67 or so, and then times this. So in cosmology, it's always kind of parameterized in units of this parameter little h, but it's just 1. I use the temperature today, which is the CMB temperature. It's 2.3 into the minus 30. GV, and I also use the number of degrees of freedom today is approximately 3.91. Okay, now you plug this all in, you put it all together. That's pretty straightforward. Then what you get. Actually, let me just leave this because I can reuse this formula. So, what you get for the energy density in gravitational waves today, the estimate is 1.9, 10 to the minus 5, h squared. So the same that we had before, just as the effect of 1.9, 10 to the minus 5. H squared. Okay, the last thing, if you give me 1 minute, then I'm done. I'm sorry for running so over time. So the other thing I have to evolve to today is the peak frequency. And I mean, this is just essentially stretching the wavelengths. So I just have to multiply this by the ratio of the scale factors at and today, and then I get this. I can use the same results as before. So this was according to beta. So now today, the peak frequency of gravitational waves today is 7. Should be also 1.7, 10 to the minus 5 hertz times beta over h at the end. this would be one for roughly the electric phase transition. You can choose a different normalization, of course, if you want. Okay, 1 second, I'm almost done. That's the factor of G star. Okay, so yeah, let's see it. Next time we will I will show you the results from full numerical calculations, and you see that this actually matches surprisingly well with this method. So, and then hopefully, okay, it's my last lecture, so then I will show you some sensitivity curves of various experiments, and then hopefully we can discuss a little bit the Kummer model, what are the discovery prospects for this model. Okay.
Thank you. More questions? For Benedict? Benedict?
Not sure. I think I forgot my factor here. Forgot the pi. Not very important factor.
Okay. So, have a nice weekend, everyone. And see you on Monday at 1, right?
Yeah.
1:30.
It's 1:30 or 1? I think.
I know it around 1:30. There was.
I think it was 1 because we have to finish at 2:30 because we have a meeting at 3. So we better.
Why?
We have a meeting at 3.
Yes. But if you have meeting at 3, we can finish it.
No, we have a meeting.
I may go a little bit over time, yeah. So
Yeah, maybe a little bit over time, so better.
especially because my last lecture, it's
Yeah. Yeah. So let's make it at 1, okay?
Okay, 1, okay. Monday at 1.
Monday at 1.
So I will have to drink coffee.
What?
I will have to drink coffee.
Of course. Here we can drink coffee.
I came a little late today.
So we